fx, we need to show that this function is a Riemann integrable on closed interval 0, 1. And also we need to show this integration to be equal to 1 by 2. Before starting up with the solution, let's recall one result that a bounded function f is defined on closed interval ab is Riemann integrable if and only if the limit on the upper Riemann sum is equal to the limit on the lower Riemann sum is equal to this integral from a to b on fx, right? Where we need to take the limit that mu p is tending to 0. What is mu p? It is the mesh of p, that is the greatest length of the subinterval, right? Okay, let's start with the solution. Let's take p to be the partition, that is x0, x1, x2, x3 up to so on up to xn, right? So this be a partition of closed interval 0, 1 into n equal subintervals. And what is the length of each subinterval? That is b minus a divided by n, where a is 0 and b is 1. So this is equal to 1 minus 0 divided by n, that is equal to 1 by n. And then we are writing the points of the subinterval. The first point, that is x0, always taken to be 0. And then x1 is 1 by n, x2 is 2 by n, x3 is 3 by n, up to so on. Xi is I by n, and xn is n divided by n, that is equal to 1. This, right? Okay. Now writing the subintervals, that is from 0 to 1 by n, and then from 1 by n to 2 by n, and then from 2 by n to 3 by n, up to so on. I minus 1 divided by n to I by n, up to so on. N minus 1 divided by n to n by n, that is 1. So these are the subintervals. What is the function given to us? It is 1 minus x, right? We need to show first that this function is bounded function. So this is a given function in closed interval 0, 1. That is x is greater than equal to 0 and less than equal to 1, right? Okay, let's multiply with minus 1 all over. We get 0 minus x minus 1, and when we multiply with minus 1, the sign changed, and then adding 1 all over, we get 1 greater than equal to 1 minus x greater than equal to 0, right? And this is your function fx. That is, our function is bounded in 0, 1. Now we need to find the lower Riemann sum. It is summation I going from 1 to n, mi into the length of the ith interval, that is xi minus 1, right? And now we need to calculate this mi, small mi, and also the capital Mi for upper Riemann sum. Now x is lying between xi minus 1 and xi. Now x is lying between xi minus 1 and xi, right? To make the function fx to be equal to 1 minus x. So we first multiply all over with minus sign, or you can say with minus 1. So this is minus xi minus 1, this is minus x, and this is minus xi, and the sign changes. And then we need to add this 1. So this is 1 minus xi minus 1 greater than equal to 1 minus x greater than equal to 1 minus xi. That is 1 minus xi minus 1 is greater than equal to this f of x greater than equal to 1 minus xi. Or we can also write this as f of x is greater than equal to 1 minus xi and less than equal to 1 minus xi minus 1. So it is very clear that this is your small mi and this is your capital Mi, right? So small mi is 1 minus xi and capital Mi is 1 minus xi minus 1. Let's put the value of mi in LPF. So LPF is equal to summation I going from 1 to n, small mi, that is 1 minus xi, into the length of the ith subinterval, that is xi minus 1. So this is equal to summation I going from 1 to n, 1 minus, what is the value for xi? It is I by n. So this is I by n. This is also I by n minus xi minus 1 will be I minus 1 divided by n. Solving this we get I minus I plus 1 divided by n, that is 1 by n. Taking this 1 by n outside of the summation, and the summation is on 1 minus I divided by n. So this is equal to 1 by n, alright. Put I equal to 1 over here, we get 1 minus 1 by n plus put I equal to 2, likewise 1 minus 3 by n up to so on 1 minus n by n. So 1 plus 1 plus 1 plus 1 is up to n times. So this is n minus, taking 1 by n outside, and this is 1 plus 2 plus 3 up to n. Sum of the natural numbers is equal to n into n plus 1 divided by 2, right? So this n cancelled out with this. So this is further equal to 1 by n into 2n minus n minus 1 divided by 2. That is equal to 1 by n. So this is n minus 1 divided by 2, or you can also write this as 1 by 2 into 1 minus 1 by n. I have taken this n to the denominator of n minus 1. So we get lower Riemann sum to be equal to 1 by 2 into 1 minus 1 by n. Now calculating the upper Riemann sum. So this is equal to summation I going from 1 to n. Capital Mi is 1 minus xi minus 1 into xi minus xi minus 1. So this is equal to summation I going from 1 to n. 1 minus xi minus 1 is I minus 1 divided by n into I by n minus I minus 1 divided by n. So when solving this we get I minus I plus 1 divided by n, that is 1 by n. So this is equal to summation I going from 1 to n. 1 minus I minus 1 divided by n into 1 by n. Taking this 1 by n outside of the summation, and this is 1 minus I minus 1 divided by n. Taking the summation inside, so this is 1 by n. Summation on 1 is n minus 1 by n. Again taking this summation inside, so this is 1 by n into n minus 1 by n into, this is 1 plus 2 plus 3 up to n minus n. Sum of the natural numbers, it is n into n plus 1 divided by 2 and then plus n divided by n. So this will be 1. This n cancel out with this, and we are having 1 by n into n plus 1 minus n plus 1 divided by 2. That is n plus 1 divided by 2, or we can also write this as 1 by 2 into n plus 1 by n, which can be written as 1 by 2 into 1 plus 1 by n. So this is the upper Riemann sum. Third step is we need to find the lower Riemann integral, that is equal to limit mu p tends to 0 on the lower Riemann sum. So this is equal to limit, what is mesh of p? This is the greatest length of the subinterval, because length of each subinterval, that is every subinterval, is 1 by n. So mu p is 1 by n here. And when mu p tends to 0, this means 1 by n is tending to 0, that is n is tending to infinity. So we write here limit n tends to infinity on lower Riemann sum. What is lower Riemann sum? It is 1 by 2 into 1 minus 1 by n. This is your lower Riemann sum. So this is 1 by 2 into 1 minus 1 by n. So this is equal to 1 by 2. Limit n tends to infinity on 1 minus 1 by n. That is equal to 1 by 2 into 1. So this is equal to 1 by 2. And now finding the upper Riemann integral, that is equal to limit mu p tends to 0 on upper Riemann sum. So this is equal to limit n tends to infinity. Why? Because we know that mu p is tending to 0, that is 1 by n is tending to 0. And that implies n is tending to infinity. So what is the upper Riemann sum? it is 1 by 2 into 1 plus 1 by n. So this is equal to 1 by 2, limit n tends to infinity on 1 plus 1 by n. So that is equal to 1 by 2. When applying the limit, we are getting here 1. So this is 1 by 2. So the lower Riemann integral is equal to the upper Riemann integral, right? Both the integrals are equal. That means f is Riemann integrable. Because f is also bounded, let me write this first. Thus, lower Riemann integral is equal to the upper Riemann integral, which is equal to 1 by 2. So this implies fx is Riemann integrable. And because f is also bounded, so according to the result we have recalled in the very start of the solution, the integration from 0 to 1 on fx dx is equal to these lower and upper Riemann integrals, that is 1 by 2. So we have shown this, and here ends up the solution. Okay, thank you, stay blessed.